Okay, hello Year 12 doubles. Sorry, this is the second video I've done on this topic today because, yeah, I had a nightmare on the first one. But I have already done all the work on the whiteboard, or much of the work on the whiteboard, so that's kind of nice. Now, this topic, this entire chapter, is called Volumes of Revolution. And it's about what would happen if we took a function, and I've just drawn a function which looks like y equals kx here. It's a straight line function. What would happen if I revolved it around the x-axis? Now, what that means is if you take any point on this curve, let's take a point like, say, up. Well, let's take a point like here. Should I do it in a different color? It might be nice doing it in a different color. So let's take a point on this curve here, this blue point here. What would happen if we kept it the same distance away from the x-axis, but dragged it around in a circle? And it's the same for a point here, kept it the same distance away from the x-axis and dragged it around out of the page, if you like. It's coming out of the board and revolving round in a circle. What shape would that make? Now, I hope you can see for this first one, it's going to make you the shape of a cone. Yeah, it's going to come round like that. It's going to give you a cone shape because all the points have gone round in circles, haven't they? They've all gone round in circles according to their distance away from the x-axis. So those ones aren't so far. So it's going to give you a cone. And this is a bit like pottery, this topic of volumes of revolution. You always end up with like nice vases and cones and different shapes like that. Let's talk about another one, just so you get an idea of what a volume of revolution is. What would happen if we took a curve like this? It looks like a quadratic curve, something like x multiplied by, yeah, let's actually write down the function. Maybe the function's x times by 6 minus x or something like that. And then you get, quadratic parabola like that. What would happen if we revolved that 360 degrees around the x-axis so it's coming out of the page? What what would be the shape of the volume produced? Well, I hope you can see it would kind of be like a rugby ball this time. You'd end up with like a pointy bits at the end, but you'd end up with like, kind of a rugby ball shape. It would be circular in a sense, but it would taper both at the start and at the end. So something like that. I'm trying to show like the three-dimensional nature of the object. It's hard, obviously, drawing in 3 dimensions. I don't find it particularly easy either, but that's going to give you the shape of a rugby ball. Okay, let's do one where we've just got any old function like this one. And we're revolving it just from A to B here. So ignore that part of the curve and this part of the curve up here. We're just revolving it from A to B. What kind of shape is that going to be? Well, it's going to be kind of like a vase because you're going to have something like this. It will be symmetrical in a sense as well. It'll be, a little circle on the bottom. Yeah. And it's going to be round all the way around. Do you see what I mean? It's going to make a lovely little vase, for your flowers. So that's what a volume of revolution is. It's where you take the curve out of the page, off the board, off the plane that you're drawing on, and revolve it 360 degrees so that you create a volume. Well, the topic of volumes of revolution is all about how we can work out that volume using integration, because in the same way we can find the area under that curve, we can do something similar with a volume. So let me give you a quick justification why that might be the case. Do you recall this fact, yeah? And I haven't rubbed this off the board, sorry, maybe, yeah. Well, let's just have a look at this. Do you recall that if I'm working out the area here, what I'm really doing is finding the sum of infinitely many rectangles where the width of the rectangle is infinitely thin. So we're going to call it dx, and the height of the rectangle is y. We can consider it a rectangle and not a trapezium because as dx gets really, really, really small, the difference between those two heights is going to be negligible. And so what we're really going to be doing is the limit as dx tends to 0, that's just telling me my rectangle is getting infinitely thin. Let's find the sum, this means the sum of the rectangles, of y times delta x. So that is going to give me the area of each rectangle from A up to B. And that is the sigma definition of the integral, which is just y dx from A to B. Well, we can do a really similar thing with these volumes of revolution. What you've got to think of it as is a disk, yeah, a cylinder, if you like, because if we're revolving it around the x-axis, we're going to make, and I've drawn a picture of it down here, it's not very good, we're going to make a cylinder. Oh, that's what I need. We're going to make a cylinder go away, from this being revolved around. Each one of them is going to be an infinitely thin cylinder, like a little disc. Now, what's going to be a radius of my disc? It's going to be y. And how am I going to work out the volume of the disc? Well, surely it's going to be pi y squared multiplied by the height of the disc, because it's basically a formula for a cylinder, so pi r squared h. Well, that's going to be pi y squared dx from a to b. And that's going to give us the integral formula, pi integrate from the limits of a to b y squared dx. And that's what you need to know for revolving around the x-axis. It works for any function as long as it's being revolved around the x-axis by 360 degrees or 2 pi radians. That's essentially what we need. I've never seen, by the way, an exam question where they ask you to justify why that's a formula for a volume of a revolution, but I think it's important that you should have at least an intuition about where this formula is coming from. So yeah, it's just about the volumes of the infinitely thin disks being summed together. Okay, let's try and use this. Let's do a question, and I'm actually going to rub all this out because I wasn't happy with the way I did it before. So let me just get rid of this. This is actually question 8 from page 75. It's one of the toughest questions in the exercise, and that's why I'm choosing to do it, because it's quite tricky. You get a little picture. You get told that this has been revolved around the x-axis by 2 pi radians and that the volume equals 657 pi over 160, and you're asked to find the value of A. So that's what we're going to do. So we're going to need to use a formula here. The formula is V equals pi y squared dx. You always need a volume of revolution formula in a question on volume of revolution. So I'm going to write that down first. V equals pi y squared dx. Now your limits should be the limits for where you're revolving around on the x-axis. So that's going to be pi times pi between 2 and a. Now you need to take y squared. Don't forget to square the y. It's very easy to do that. I did that on my first video, which is one of the reasons why it went wrong, but it went wrong for several others as well. And that's going to be equal to our volume, which is 657 pi over 160. You can straight away, I suppose, cross out the pi's on either side because they're going to cancel. We're going to need to multiply that out. So let's actually multiply it out before we integrate it. So we've got 4x squared minus x to the 4 with respect to x between 2 and a. And now I can integrate. You're going to get 4x cubed over 3 minus x to the 5 over 5 between 2 and a. Give ourselves some more space. It does take a while, this one, with the tidying up, and it is one of the toughest in the exercise, so I thought I'll show you what a nasty question on this looks like. Perhaps not a good idea showing you it first, but it's okay. You're a clever class, so I'm sure you can keep up. Okay, so what do we get next? Well, we've integrated it, so let's plug our limits in. You're going to get 2 cubed 8, 32 over 3 minus 32 over 5 minus 4a cubed over 3 minus a to the 5 over 5. Okay, so I think what I'm going to do first is I'm going to combine that on my calculator. Might as well just do it on a calc. What do you get? 32 over 3. You know, the number's so awkward, you might as well pick up your calculator in this kind of thing. 64/15. And you might as well simplify that. That's going to be 20a cubed minus 3a to the 5 over 15. Might even choose to multiply everything by 15, to be honest with you. Looks like the thing to do. So 657 times 15 divided by 160. You're getting 197. Horrible numbers in this question. Over 32 equals 64 minus 20a cubed plus 3a to the 5. This looks horrible as well. It's a quintic equation. That's why I think this question is actually really, really hard. We'll take the numbers all to one side and we'll make it look like a typical polynomial. I'm going to have to do 64 minus that last answer. 77 over 32. And I suppose I might times everything by 32 at the end. So 96a to the 5 minus 640a cubed plus 77. Yeah. Now, when I look at an equation like this, and this isn't typical of volumes of revolution, by the way. Normally you've finished the questions by now and it's easy. But, this has got a weird little quirk at the end where it's saying, how do you solve a quintic? And the only way we've got at A level is by numerical method, but if they want the exact value, factor theorem. Now, if you go back to the diagram, what could A be? I suppose it could be 1. So try 1. Is 96 minus 640 plus 77 0? No. So what else could you try? Well, a half or 1.5, yeah? And when you try a half, it actually works. And there's no other way, there's no nice way of doing that. You're just stuck with having to do it like that. So you've got to do 96 times a half to the power of 5. I know this works because I did it in the last video. Minus 640 times a half to the power of 3 plus 77. And then, wow, it's 0. And so you can say kind of, if you like, by inspection, A equals a half. Yeah, that last bit of the question I think is really quite unfair, but it was in an exam paper. I don't know which one it was in. It must have been in quite a tough level, or maybe it was, I don't know. I don't know where they got it from, but like this, what else could A be? Like you've got to take a guess there, like because factor theorem is guessing theorem, isn't it? And that's the only way we've got of solving those. So yeah, you get A equals a half. Okay, let's try. Let's quickly introduce you to the next topic in exercise 5b. It's just volumes of revolution around the y-axis, yeah? Well, this just works back to front. Everything's back to front. This time the formula is v equals pi x squared dy. Notice it was pi y squared dx last time. Well, all the y's and x's just swap over. The one thing to be wary of is bear in mind your limits now aren't on the x-axis. They should be on the y-axis because we're revolving it around the y. This particular one, if I revolved that from A to B around the y, I'd kind of make a weird looking vase like that, which tapers at the end. But yeah, I get v equals pi x squared dy. And this is the formula I'm going to use. Now I'm going to do a question. I'll write it all down for you again so I can sort of explain my thinking as I go. But this is taken from question 3, and it's not question 3 part A, it's question 3 part B. So I just want you to be aware of that. I'm going to do question 3 part B, where I'm actually revolving it around the y-axis. Question 3 part A, they just get you to find an area. They don't actually revolve it around the y-axis. So let's do this one. And this one's going to be a bit more straightforward than the last one in some sense because we haven't got to do it backwards. We're going to actually find the volume of revolution. So what we're going to do is we're going to revolve that region R around the y-axis by 360 degrees. And the formula is v equals pi x squared dy, and these have to be our y limits, so they are 9 and 4. Cool. Okay, what is x squared? Because this is telling us to integrate with respect to y. So we've got to put everything in terms of y. So we'll have to square out that first, and that's going to give us y plus 1 over y to the 4 plus root 2 times root y over y squared, yeah? dy between 9 and 4. Let's simplify that a little bit. We're going to get between 9 and 4. The y is no problem. Well, 1 over y to the 4 is no problem because it's just y to the minus 4. This is going to become 2y to the minus 3 over 2 with respect to y. Don't ignore the dy's and the dx's. You'll lose marks for it. I would definitely take a mark off. Okay, now let's integrate it. Y squared over 2 minus y to the minus 3 over 3, because it's over minus 3. And then this is also going to be a minus, but we're going to be increasing 2y to the minus a half over a half. So that's going to be the same as 4y to the minus a half between 9 and 4. Personally, I'd definitely use a calculator now, but I wouldn't ask my calculator to do too much at once. So I'm going to be 9 squared over 2 minus 9 to the minus 3 over 3. Minus 4 times 9 to the minus a half. I've done the 2 divided by a half in the head there. Minus, okay, 4 squared over 2 minus 4 to the minus 3 over 3 minus 4 times by 4 to the minus a half. Yeah. Okay, work those out bit by bit. I'm going to do the first one in my calculator. So I'm going to press 9, enter. Then I'm going to do answer squared over 2 minus answer to the minus 3 divided by 3 minus, and it does take a little while. I suppose you could do 9 to the minus a half in your head, couldn't you? Because that's just going to be a third. So it's going to be minus 4/3. Okay, I get 39.166. They want the answer to one decimal place here, so I don't have to worry too much about accuracy. Now I'm going to do the same with a 4. 8 minus 4 to the minus 3 divided by 3 minus, what is that? 4 times a half, so that's going to be minus 2. And I get 1151 over 192 on my calc. And then work that all out. So 39.1662 minus answer times by pi. Okay, and I'm getting to 2 decimal places as the question asks for it, 104.21. Okay, I hope that helps for volumes of revolution. Best of luck with this topic. Do get in touch if you get stuck on any of it. I do want to get this chapter done and the next 2 chapters done before the summer, so let's crack into it. Okay, keep up the hard work and let me know if you get stuck. Bye bye.